So today we're going to get into our second type of bonding. We've talked already about ionic bonding, so now we're going to go turn our attention to another type referred to as covalent bonding. So our first question here is, how exactly are covalent bonds different than ionic bonds? Well, with covalent bonds, the idea is still the same. These atoms want to have a full octet, meaning they want to have that full outer shell, so typically 8 valence electrons. However, ionic bonds, we saw the electrons are actually being given and taken between the atoms, but in covalent bonds, these electrons are being shared between atoms. So it's not like one atom is taking the valence electrons from another one, but rather they're both having ownership to them. I'll talk a bit in a moment about exactly why that happens, but just know here, no electron transfer is happening. Okay, this is all about how the electrons are being shared rather than moved. Ionic bonds have a metal and a nonmetal component to them typically, whereas covalent bonds are the bonds between two nonmetals. And just one last little thing here, ionic compounds, whenever we do have one, we refer to them as formula units, but covalently bonded compounds are referred to as molecules. So it's pretty much a really common thing where everybody wants to call every single chemical compound a molecule, but molecules are actually reserved for anything with a covalent compound. So basically, that's something made of only nonmetals. So going back to the electrons being shared, let's take a look at our electronegativity table. So we know that elements on the left side of the table have a low electronegativity, meaning that they don't really want electrons, whereas elements on the right-hand side have a higher electronegativity, so they really want to gain electrons. They have that higher desire. So if we're talking about covalent bonds between nonmetals, we're basically talking about elements over here on this right-hand side of the table. So that means everything here is going to have more or less a high electronegativity. So that means when it comes to forming bonds and wanting to have those full octets, just about any combination of element here is going to want to have the electrons. They're not going to be as willing to lose them as some of the metals are. So rather than one element lose, another one gain electrons, the only way this kind of agreement works is if both elements share the electrons. So these nonmetals, who typically have a high electronegativity and thus want to all more or less gain electrons, they have to actually learn to share with one another instead of one of them having to give it up to another one. Now, this sharing is not equal. That's something that we're going to get into later on, where these atoms, we do have to take into account their electronegativity, but just know for right now that the covalent bonds have the sharing of electrons because these nonmetals all have their own high electronegativity, so they don't want to be the ones to lose their electrons. So our molecular formula is essentially the formula for a molecule. Much like the ionic compound, it just kind of gives you how many atoms of each element are going to be present. One thing here, it does not actually tell you how the molecule is structured. Okay, so in the formula, you'll know all about how many elements and how many atoms there are, but you have no idea how these things are connected. And here's just some examples of molecular formula. We have NH3, H2O, CO2, H2SO4, C6, H12O6, which is kind of different things here. Many of these are common things like water, carbon dioxide. This is our sugar. Okay, all of these are covalently bonded together. So when we get into the formula and the names and molecular compounds and just compounds in general, they actually abide by two laws. So these laws are called the law of definite proportions and the law of multiple proportions. So these to kind of help govern how these compounds are named and the formulas behind them. So the first law of definite proportions states that if you have a chemical formula, that will tell you the fixed ratio of atoms and elements to one another. And that means if you always have that same compound, that ratio is always going to be the same regardless of how much of that compound you have. For example, H2O is made out of two hydrogen atoms and one oxygen atom. Meaning, if I ever have a 2 to 1 ratio of hydrogen to oxygen, it's going to be H2O. Rather, that this ratio is going to be fixed for this compound. You can also look at it as a ratio of the masses to one another, that if I have two hydrogen and one oxygen, that ratio of the mass is basically going to be a 1 to 8 ratio. And it's going to be the same for H2O, meaning every time I have H2O, it's always going to be either 2 to 1 atom ratio or 1 to 8 mass ratio. So that's what it says. The proportion or the ratio of a compound can never change if we're talking about the same compound. Doesn't matter if I have like 10 water molecules, that 2 to 1 atom ratio is always going to be the same. For the law of multiple proportions, well, this addresses exactly the reason that these different compounds may have the same elements in them, but they'll be in different ratios to one another. Meaning here, if I have the same elements, they don't always have to combine in the same exact way. For example, water, H2O, and peroxide, H2O2. These are both combined of hydrogen and oxygen. But water has a 2 to 1 ratio of hydrogen to oxygen, whereas peroxide has a 2 to 2 ratio. So this law says that elements are actually able to combine in different proportions, that they don't always have to be in the same exact ratio. Okay, so these two laws just kind of go over our different formula, just the ratio, the ways that these things combine together. Okay, so they just kind of dictate some of the laws that go into these formula and things behind them. So then let's move on to naming molecules. Okay, we know what molecules are, but know about the covalent bond now, the sharing of the electron. So then if molecules can take different ratios of the same elements, how exactly do you distinguish their names? Well, because of the fact that these electrons are being shared rather than actually given and taken, there are no ions. There's no plugging off the electron and forming ions in a molecular compound. So when we have a molecule, we don't ever discuss ions because ions are not present. The electrons are still a part of that element, but instead, now these atoms are sharing them. Okay, so we don't discuss charges, we don't talk about cation, anion, it's just these two elements are sharing the electrons. So the naming is actually really simple, much like how we had the ionic compound, basically the names of the two ions here. The molecule name is just the name of the two elements involved. Okay, and it just kind of tells you which elements are involved and how many atoms of every element are present. So to identify how many atoms are present of every element, we need to use a prefix. So the prefix thing that goes before the word, here are prefixes up to 10. So we're going to be using these prefixes to basically tell us how many of each element are there. One thing to keep in mind is that the last element or the second element still has to have that "ide" ending to it. So just like how we saw for anions, they take an IDE ending. The second element in a molecule also takes that "ide" ending. This does not mean it's an ion. Okay, so it's not an ion here, but rather that's just how it's named. Okay, and just one exception, when you use the prefixes to tell you how many of each atom is present, you never ever ever use mono as the first word or the beginning to a name. You can use mono for the second element listed, but never for the first element listed. Okay, so let's take a look exactly what I mean here. If I have a molecule like CO, okay, the two elements here are carbon and oxygen. I have one carbon and I have one oxygen. So typically for one, we would use the mono prefix. Okay, rule says you can't use mono to begin. So I'll go ahead and name it carbon. By writing just carbon, it tells me I have one carbon. I don't add a mono to the front. But I have one oxygen. So I can use mono for the second element. So oxygen, the ending has to change to an "ide," so oxide. If I have one of those, it's monoxide or one oxygen. So one carbon, one oxygen takes the name carbon monoxide. This basically tells me one carbon, one oxygen. Now if I have two oxygens, it makes CO2. Again, I have one carbon. We don't use mono. So one carbon, so just carbon, and now I have two oxygens, so I'm going to use this prefix di. Okay, so it becomes carbon dioxide, which means one carbon, two oxygen. Okay, second example, third example here, sorry. We have two nitrogen, five oxygen. So nitrogen and oxygen are my two elements. The two nitrogen means I take a di, so dinitrogen, two nitrogen. And then penta is the prefix for 5, so pentaoxide, so dinitrogen pentoxide tells me 2 nitrogen, 5 oxygen. And then here's something familiar, H2O. Again here, 2 hydrogen, 1 oxygen, so dihydrogen monoxide, 2H1O. Okay, so it's really simple. First element's name does not change. Second element takes an "ide" ending, and then you just add a prefix telling you how many atoms of each are present. Now these are kind of like their scientific names, but a lot of these compounds actually do just have common names to them. As we're familiar, like no one goes around and says H2O, like I'm gonna have some dihydrogen monoxide. Rather, they just say we have water. Okay, so not all of the scientific names are always going to be used, but this is how you properly name covalently bonded compounds. Okay, so why don't you go ahead and practice now? Write the name from the formula for these molecules, and then write the formula from the name. Okay, and here are the answers here. So again, you can see in the name, the first element does not change the name. The second element takes an "ide" ending, and then you just add a prefix whenever you are talking about how many atoms are present. Same thing down here. The names basically will tell you how many atoms are present and kind of the order that they go in. All right, so then the last question that we want to address, well then, how do you tell an ionic and molecular compound apart from each other? So how can you tell what kind of bond a compound is going to have? And then what kind of naming to use? Well, it's really easy. An ionic compound is typically going to be a metal and a nonmetal combined. The electrons are transferred in that, whereas molecular compounds are going to be two nonmetals and electrons are shared. So if you want to know what kind of compound you have, thus what kind of naming to use for a formula if you're given, well, it's just kind of taking a look at the elements present. Okay, so if you have a metal present, then you're essentially going to have an ionic compound. Okay, so then once you know what kind of combination or types of atoms you're going to have, that's when you know what kind of naming to use. Okay, so just here to practicing, taking a look at identifying ionic or molecular compounds. So just tell me which one is going to be ionic or which one is going to be a molecule. And here's answers here. So you can see that anything with a metal, like sodium, calcium, copper, all of these have got the ionic label to them because it is a metal. The second part is a non-metal. Even down here, the Mg3PO4 too. Magnesium is a metal. PO4, these are all non-metals. So you can think of that phosphate ion as also being a non-metal.